Hey everybody! Today we get to talk about an extremely exciting result. This is, in a many sense of the word, the culminating result of our early work on planar curves. As you know, we've looked at curves in the plane, we've looked at many different examples and many different properties of curves in the plane, with a sort of extra emphasis here at the end on curvature. It turns out that that emphasis is well placed because curvature, in a very real sense, is the defining characteristic of a plane curve. In other words, if we know the curvature of our plane curve, we know just about every meaningful thing, or we can discover every meaningful thing about that curve. And this is because curvature will allow us to reconstruct what our original curve was. Or in other words, given a sense of what our curvature function looks like, we should be able to find a plane curve that has that curvature. Let's take a look at the more precise result, which is important enough that we give it one of the fundamental names. This is the fundamental theorem of plane curves. The theorem reads as follows. Given any piecewise continuous function, which I'll suggestively name kappa, but given any piecewise continuous function kappa, there exists an x of t, a regular curve parametrized by arc length, that has kappa as its curvature. Right? So given any piecewise continuous function, we can find an x of s, actually, because it's parametrized by arc length, an x of s whose curvature is that function kappa. Right? So this gives us an existence result telling us that such a plane curve does in fact exist. We also have a uniqueness result. So this is both existence and uniqueness. This tells us that not only do we have such a curve, but furthermore, this curve is unique up to isometries in the plane. So what is this telling us sort of practically? Right? Well, let's take a look at this picture down here. I'm going to scroll down. All right. So this is a sort of schematic that we become familiar with at this point. Suppose we have a parametrized curve x that's drawn here in red, and it's parametrized by arc length, so we're using s as our parameter here, right? So we're mapping from s into the xy plane. I want to pause and think specifically about the curvature function of this curve, right? So the curvature function kappa will probably, as we trace through the curve, it'll start off being positive, because our curve is curving in the positive direction, the counterclockwise direction, but it'll quickly become 0, then it will become negative as we curl clockwise, and then it will continue to be negative, but maybe it'll be really negative up here when we're curving very quickly, and then it'll be a little less negative down here as we're curving more slowly. So if I wanted to graph this curvature as a function of s, it would probably look something like this, and here I've drawn it in green. So it starts off pretty positive, relatively quickly becomes negative, and then is negative for a little bit, becoming less negative as we go forward in time. Okay, so this is what we've done in the past. We've taken a curve and looked at its curvature function. The fundamental theorem of plane curves allows us to go in the reverse direction. It says, given any piecewise continuous curvature function, so given this function, I can guarantee the existence of a function like this, of a parametrized curve that looks like this. Maybe looks like this. Furthermore, any other plane curve that has this as its curvature function will look identical to this modulo, or up to, an isometry of the plane, right? So it's possible we could be looking at a different curve, but it might have a different start point, or it might have been translated or rotated somehow. So for example, something like this. We could end up with a curve that looks the same up to a rigid motion or an isometry of the plane. So that is a pretty big result, and in this video, we're going to talk through the proof of this result. Okay, so here's our proof. Right? We're going to start just by listing some facts that we know about any parametrized curve. And then specifically in red, we'll identify moments when we are looking at a particular curve parametrized by arc length. All right, so for any curve x, right, we can write x as its two coordinate functions, x and y, and x prime will just be x prime comma y prime, we can observe, right? We can observe that in fact x prime will equal our unit tangent vector t when we are parameterizing by unit speed. So if we're using s as our parameter, then x prime of s is really nothing more than t of s, right? And again, the reason for that is that our t of s is just our x prime of s divided by the speed at which we're parameterizing, right? Divided by the norm of x prime of s. If we're using unit speed, then this is just divided by 1, and so these two quantities are identical to each other. And so here we have sort of a schematic picture of this, right? We have our x of s, we have all of these unit tangent vectors, aka our x primes. And a big idea that we're going to use is we're going to introduce this new variable, theta. And specifically, theta is going to be a measurement of angle. Because all of these red arrows have length equal to 1, because, again, we're at unit speed. Because each of these have length equal to 1, the real distinguishing factor between each of these arrows is the direction that it's pointing in. And we're going to identify that by using an angle theta. And to keep it, nice and standard, we're going to identify theta as the angle that our arrow makes with the positive x direction. Right? So in all of these, looks like I'm having theta values that are slightly negative. That's a-okay. If I picked different arrows to draw, right, they might have been positive. But currently, right, I'm identifying each of these arrows by a particular angle theta. And because our curve is moving in s, because these arrows are changing in s, I can think of theta itself as a function of s. So theta of s measures the angle that is formed between the unit tangent vector and the positive x-axis at time s. Now, what does that tell us, right? Sort of going back up here, I guess, or using the same set of equations, we have that x prime, which we said was equal to t, is equal to x prime comma y prime, and that is equal to cosine of theta comma sine of theta, because again, once we know this angle theta, the arrow is just pointing in the direction of its cosine comma its sine. So this is telling us that x prime is cosine of theta of s, and y prime is sine of theta of s. And our big next question will be, based on this framework, what is t prime, right? We had to calculate t prime originally to talk about curvature. So if we go and we calculate t prime, what we'll see is that t prime, right, t prime is equal to x double prime, y double prime, but that is going to equal, if I take the derivative of this, right, and this is an s derivative, then by the chain rule, this will become negative sine of theta of s times theta prime of s. And then the same thing over here, we'll get cosine of theta of s times theta prime of s. Right, so according to the chain rule, we get this extra piece here. And this will equal, to consolidate this a little bit, I'll factor out this theta prime of s. So we get theta prime of s, times theta prime of s times negative sine of theta cosine of theta. Ooh, and if we're really observant and really clever here, we can notice that this vector, negative sine of theta comma cosine of theta, right, let me actually give that a color. Let's call that yellow, right? Negative sine of theta comma cosine of theta is exactly the vector that is normal to the curve in each of these cases. right? So it's the vector that makes a 90-degree angle with our previous red arrow. In other words, this is our u from before, our principal normal vector. So this whole thing is equal to theta prime of s times what amounts to u. And that is huge, right? So this is all, again, this is all sort of preliminary computation. We're about to be ready to get into the heart of the proof. But why is this huge? This is huge because we already knew, right? And let me separate this a little bit. Right? We already knew that t prime of s was equal to kappa times s prime times u, right? Where t prime and u are our vectors. We should actually, right? Keep the notation looking good, right? Those were vectors. And this piece here, the s prime, was the speed. When we're parameterized by unit speed, this just becomes the s derivative of s, and that just equals 1. So since we're parameterizing by unit speed, this piece goes away, and we get that t prime is equal to kappa times u. So taken together, we have t prime equals kappa times u. Up here, we have t prime equals theta prime times u. And so taken together, we have that our kappa function is exactly equal to our theta prime. That's the end of the setup, but that is hugely important. And now we see why, right? So again, sort of thinking forwards, right? If we started with an x, we would take the derivative x prime, which would be cosine of theta comma sine of theta, and also x prime comma y prime. We have this relationship between x prime and y prime and our angle theta. And we've just seen that theta prime is equal to kappa. So going back to the fundamental theorem, right, the statement of this fundamental theorem, if we are given a kappa, given a piecewise continuous function kappa, we can integrate it, and we'll actually need to integrate twice here to recover our original x, our original parametrized curve, right? And so to see this, again, sort of working backwards, we're going to start by integrating kappa to calculate our theta, right? To calculate our angle. And specifically, the fundamental theorem of calculus says that I can find an antiderivative of kappa. It's just going to be this, antiderivative here plus some additional constant. Once I have figured out, so that's one integration. Once I have figured out what my theta is, I can go back here, right? So now I know what cosine of theta and sine of theta are, and I can integrate again. I can integrate each of those to recover my original x and y functions. So x of s, little x of s, is just the integral of cosine of theta plus a constant, and little y is just the integral of sine of theta plus a constant. And finally, right, we have that our capital X, right, our parametrized curve, parameterized by arc length, is just given by the x of s and the y of s that we previously calculated. So we ultimately had to take two derivative levels, right? First to integrate kappa to get theta, and then to integrate theta to get x and y. And notice we do have these extra constants here. I don't want them to just completely float away, right? These pieces here are all additional constants. And here's where the uniqueness up to isometry comes in, right? Because this theta was telling us something about the angle that our curve is making at any given moment. And adding an additional constant, right, this additional constant will correspond to a rotation of our curve, right? So a rotation of our curve will be a rotational isometry. And similarly, this plus e and this plus f, these constants will move our starting position in the xy plane. And therefore, these constants taken together give us a translational isometry. So these three constants are actually crucial to the uniqueness up to isometry, and specifically, they help us determine whether or not there is a rotation or a translation occurring. So with that, though, we now have a framework for how we can take our curvature function kappa, or a curvature function kappa, and reconstruct a unique, up to isometry, a unique parametrized curve that has that curvature function as its curvature. Awesome. Awesome.